Hello. We are going to discuss the situation today.
We'll be discussing the binary model within the context of time series analysis, and as is our usual practice, we will be demonstrating how to apply this effectively using our dedicated online platform, the Finance Research Gate website.
But as is our usual custom, we always begin by laying out the theoretical foundation.
So the binary choice model is the model in which the y variable can only assume one of two possible outcomes. For example, either a success or a failure, or whether an event occurred or it did not occur. So essentially, we're presented with just two distinct possibilities. Either something occurred or it simply did not happen at all. Therefore, we can represent this as a 1 or a 0. This fundamental concept truly defines what a binary choice is.
And the forecast will be placed firmly within the context of a time series.
For instance, this could prove quite useful within the field of finance should one wish to accurately model whether a monthly stock return is expected to be positive or perhaps negative. This is important because if we can predict, or if we have a model to predict whether a stock's return will be positive, then we can devise a successful investment strategy. Or, as an economist, we can make use of the Logistic or the Probit model. These are the two distinct variations of the binary choice model, which we are now going to discuss. The binary model, quite simply, will also enable you to forecast whether the economy will be experiencing a recession at a specific time t, or if a particular firm is going to default on its obligations. So, we're not interested in a specific value of y, we're interested in whether that event is going to occur or not. So, this particular one is what we call the regression model. The only real difference when you compare it to many other models is simply the y variable. It has two possible values, 0 or 1. 0 means the event didn't occur, 1 means it did. So we can use the past or specific historical observations. This will involve determining if the event took place, represented by 0 or 1 for the y variable, and we can also perform a regression using various explanatory variables. That include the regression x explanatory variable. Also, we can make this model dynamic by incorporating the lagged values of the variable y, meaning that we are modeling the likelihood of an event occurring based on its past history.
What we are using here specifically is the variable known as the lagged y. In some instances, if an event has occurred in the past, that particular occurrence may either increase or decrease the overall likelihood of that same event happening again. So this particular factor would be a highly relevant variable that we should definitely include. Anything that we cannot explain regarding the probability of the event or the variable y will ultimately be attributed to the error term. So, in this specific context, the interpretation we're focusing on is primarily concerned with the probability as opposed to trying to explain a single particular value for y. This is because the event of y occurring is either that we have 1, if the event happened or not. And that probability should be between 0, meaning that we don't expect the event to occur, not in any way, shape, or form, approaching 1, which represents the maximum possible value, meaning we are almost 100% certain that the event will certainly occur given the coefficients and the regressor values. However, when we fit that model, we are not going to get precisely 0 and 1 for the fitted value, and that is important to understand. Once we have fitted the regression model using actual data, we can then estimate the coefficients. And then, at that crucial stage, we can proceed to input our primary explanatory variable, and we'll do that in conjunction with a coefficient that has been meticulously estimated. And through this process, we will ultimately be provided with the precise result we are seeking. The predicted y. It's important to note that the predicted y is not restricted to just 0 or 1. Instead, it represents a continuous variable. The actual observed value, however, is a dummy variable that can only take on 0 or 1. Always, the fitted value derived from this regression analysis is always a continuous numerical value, or it could be considered a score values, or even an index value. The resulting index value can be negative or greater than 1, or even fractional, like 1.3 or 2.7. Such values do not represent valid probabilities. They are simply predicted or fitted scores. Now, this linear score is directly related to the probability and the actual outcome, or y, in a simple, straightforward situation. If the y variable or the fitted values from the model, I in this case is quite large or significantly high, which indicates that it's highly probable the predicted y value will be 1, suggesting that we have a very good probability of the event actually occurring. If it's low, it means that we predict that the event is not going to occur. So, the calculated or fitted y output will act as a latent variable. It's not something that we can directly observe within the raw data itself, but rather something that we generate and then subsequently utilize to determine the predicted probability. So this is essentially a concealed ongoing indicator that quantifies the inherent tendency, the underlying pressure, or the sheer strength that is actively propelling the system towards the occurrence of a particular event, or indeed towards reaching that specific state 1. For our specific example, we'd be using this particular case. The event we're defining is if the monthly stock return turns out to be positive and 0 for all the outcomes. Now, the fitted y won't be 1 or 0, it will be a continuous numbers, but that will give you a tendency for having 1 or 0. So the fundamental question we face is how we can effectively convert this into a meaningful probability score, ensuring it accurately reflects the real-world observed data. This is because we're currently dealing with only two very distinct and extreme outcomes, either a complete 0 or a clear 1.
And we are discussing the interpretation from a probabilistic perspective. Therefore, its value could be 0, which indicates that the probability is indeed 0, or it might assume an extreme value. In most situations, the probability will typically fall within the range defined by these two figures. So we have to differentiate between the actual one, whether the event occurred or not, 0 or 1, a resulting fitted score, and the underlying latent variable, the continuous numerical value that we derive from the fitted regression model, and also the probability which is very closely aligned to the occurrence of the actual event.
So our main objective here is to predict whether this event will actually take place or not. These represent the past values, the historical data points we have.
The one that we are interested in is this one, because we are using the model to forecast the probability and predict if the event will occur at time period t or not.
So the fitted score, as we've previously discussed, if it's high, it indicates that the probability is quite high. The likelihood of this particular event taking place within the specified time frame, period t, in the future is expected to be quite elevated. And to be more specific, we can confidently state that if the fitted value is greater than 0, what this signifies is that we can assert it's more likely to predict a value of 1 for the true binary outcome and a value of 0 in all other scenarios. Should the 0 value happen to be quite small, pause for this particular scenario, pause, we can then establish a threshold C. That could be 10, 5, 15, or even 20, for example. The fundamental idea is simply this. If the index or the fitted value is high, it will then translate into a higher probability. This is essentially the entire concept.
So, for instance, if we are working with a logistic or a binary model that includes two independent variables, we then proceed to estimate their corresponding coefficients. Multiply the x by the coefficient, and then you multiply the x by the coefficient. We are looking to find the y, the fitted or predicted value, perhaps 0.2 for example. Or if we follow this example, the full version that includes a constant.
If we plug in the predicted parameters, we will then obtain a result. Now let's consider a scenario where the predicted y value comes out to be, for example, 0.9. Then if we set our decision threshold, for instance, to be exactly 0, this would consequently mean that, well, so in this particular type of observation, we're predicting that the event itself actually took place. Pause. If the question is, did it truly occur or not? Pause. Essentially, we're looking at a binary outcome, either 1 or 0. So you might find yourself with an Excel spreadsheet that looks exactly like this example. This specific part here, it represents the actual true value. And this column right here is what we refer to as the y variable. And this particular element represents either the predicted or the latent variable, which is the y star that we've used here in our example. So you might get like something along the lines of, this indicates a very, very high score, as we can observe. Let me just adjust my terminology and refer to this as the probability. What we are actually looking at here is the probability that has been derived from the fitted value, which we call y. Now, this is not the y star, nor is it the latent variable. It's simply the probability that is derived from it. So, for instance, if the y value is high, then the probability would also be high.
Now, the specific observation could either perfectly match or potentially diverge from the actual established observations. For example, if it's 1 and the predicted probability is high, it means the model is working properly. This should be true for almost every observation. So how exactly do we transition from the latent equation to the actual probability statement we need to derive? Because ultimately, at the very end of this process, our primary focus is the probability itself.
I'm trying to understand the precise process. How exactly can we effectively transform a continuous fitted value, typically represented as y, into a corresponding probability?
We have two options available. We can use the logistic.
It could be a simple regression analysis or a Probit regression.
Now, the logistic regression process will simply transform our fitted y value, which in this specific case we're calling z. The primary reason that we are referring to it as z here is that in the event that
the fitted value actually has a quite different threshold than 0.
So, what this indicates is that we most likely anticipate an event occurring at this point, but that is not the case. In our specific situation, the threshold may not be 0. Consequently, the derived fitted value is expected to be substantially greater than the designated C value.
We need the probability or the predicted probability value to be much closer to 1 or alternatively much closer to 0, particularly if it falls below C.
In this particular situation, if you were to move that point or data to the left, you would then recover the initial predicted fitted value minus whatever specific threshold or minimum requirement you personally determine is most appropriate and suitable for our particular circumstances.
So what that particular process will ultimately provide you with is simply the threshold value of 0.
And we're going to assign the letter z to this particular result. It represents a newly transformed variable that originates directly from our previously calculated or fitted y value through what is considered a very simple and straightforward transformation. The main idea is that we'll use either the fitted value or the transformed one, and then we must carefully plug this result into the specific logistic distribution model in order to effectively transform the calculated fitted value into a meaningful probability measure. Because ultimately we really need to obtain a value that falls somewhere between 0 and 1 so it can properly align with the binary outcome selection of our regression model. And that is the model we are using. This is commonly called the logistic model or logistic regression. So once you fit the value in this spot, you then plug it into the equation, ensuring it's between 0 and 1. Can you tell me how this particular equation manages to guarantee that any number you input into it will always result in a value strictly between 0 and 1? Well, the idea is that this term, first, it must be greater than 0 no matter what. Whether it's incredibly large or quite small, it truly doesn't matter, because ultimately you'll still end up with this term.
And irrespective of the specific numerical quantity you currently possess, that particular mathematical element will, over time, inevitably become a positive value.
And if it's positive, irrespective of its size, whether it's a small or a large number, if you were to add it to 1, the denominator will always, without exception, be larger than the numerator.
From a mathematical perspective, it's quite evident because you are simply adding 1 to a given value. It could be a very small value, but ultimately you are adding some amount of value to the number 1, so the denominator will always be greater than the numerator, which will then translate to a ratio.
If this particular value is so incredibly small, close to 0, then the probability of it happening will be exactly 1, and that, naturally, is the extreme case. Now, if this particular value were to become extremely large, then the denominator would also grow to be quite substantial. Now, consequently, when we divide the number 1 by such an immense figure, the outcome will inevitably approach 0.
So, its value must always be bounded between 1 and 0 under all circumstances. And you can plug in values. For example, if you were to plug in -2, a value of -2 indicates that in this particular instance, we have very low probability of an event occurring. This is because the calculated or fitted value is quite small, potentially even negative. So, when you substitute the negative value in this spot, it will of course be negative times negative, which results in E. The natural growth in which is the number a, which is approximately 2.71 raised to the power of 2, and that will be the size of a number, like 7.3. You then add 1 to it, and then you will get 8.3. When you divide 1 by 8.3, the result is a very small number. It's approximately 11%,
or 0.11 as a decimal. So when you have a fitted value that is quite small, or perhaps its corresponding derived z-score, you'll find that these two measurements are indeed very close to each other. So this particular item is the original one, and then this other one is the transformed version. Consequently, if these quantities are quite small, it logically follows that the resulting probability will also be quite small.
So this is precisely how the mathematics of this equation operates. And the reverse is also true. For instance, if you were to select a positive value of 2, it implies that we should anticipate a good probability. When you input those specific numbers, you will then obtain a high probability.
When we refer to the term CDF, we are talking about what is known as the cumulative distribution function. And what this function essentially does is it will provide you with the exact probability of observing any specific value within your dataset. Consider, for example, the value of -2. At this point would be positioned at the extreme end of the distribution. So what is the cumulative probability of observing a value of -2 or less?
This is the meaning of 0.11 that we had obtained earlier.
In our +2 case, for example, we are then asking ourselves whether, or more specifically, we are inquiring about the overall probability of having a value that is 2 or any number below it. The probability, as it turned out, was quite high, specifically 0.88. This is precisely what the meaning of CDF truly represents. It's essentially a direct reflection of the information shown in this graph.
So, what is the actual difference between a logistic and a Probit model? Both of them, you see, will give you a number between 0 and 1. Yes, both of them will provide a value ranging from 0 to 1. The only real distinction is about their underlying distribution.
The Probit model, for its part, will inherently assume a normal distribution, whereas the Logit model, quite distinctly, will assume the logistic distribution. So, in essence, it's purely about the underlying distribution we're employing to ultimately obtain that probability. That is, in fact, the sole significant distinction we need to consider. Therefore, the entire discussion truly revolves around the specific statistical distribution that is assumed when we are in the process of deriving the probability. However, the fundamental underlying concept, that very same core idea, ultimately remains completely unchanged. We obtain at the end a number between 0 and 1, and that reflects the probability.
So the core concept is essentially the same. We first calculate our z-value, and then we determine the probability associated with that specific number using the standard normal distribution table.
And the normal distribution is given by this. For example,
This chart displays the cumulative distribution, extending until we reach a z-score of, for example, -2.
Essentially, the integral component involves summing up the probabilities. Just as we demonstrated earlier, this process is inherently cumulative. We are effectively accumulating the likelihood of encountering any value that falls beneath the specific critical threshold we've established.
so what we do is we sum up all the probabilities here for a value of -2. Now, for a value of 2, the corresponding area is actually even greater. Therefore, we then proceed to add the probability of obtaining a value that is 2 or less.
So essentially, it's like summing the probabilities in that particular sense. This is precisely why we have the integral part. We are taking the cumulative probability starting from -infinity, which effectively covers the entire lower tail of the distribution, and assigning it to our designated target variable. But we should be aware that this is a normal distribution. My handwriting is not clear. So how do we go about estimating the coefficients? Do we use, for example, the normal OLS? In this binary model, we use the log likelihood function, the maximum likelihood estimation, to determine the optimal parameters for our statistical analysis. We're talking about the log, specifically the log likelihood function, and then the maximum log likelihood function.
Meaning that we estimate the parameter to estimate or maximize the likelihood function. What is the likelihood function? The likelihood function will look like this.
This represents the log likelihood function. Let me explain this equation.
Let's consider that for our first observation, we received an estimated probability of 0.8, along with 0.3 and 0.6. Our objective is to assess the performance of this particular model. Therefore, we proceed to compare these results against the actual observed outcome. Now, if the estimated probability is high when the event occurs, that means we're doing a great job.
If the probability we estimate is low when the actual event is 0, that means the event did not occur, and it also signifies we are doing a good job. Here also, if we have a good probability for the actual event, it means that we are doing a good job. So the idea is we want to estimate the model. Our goal is to maximize the match in this situation. The final outcome of this match right here will be assessed and calculated as a single distinct number by simply adhering to this precise equation. Conversely, if the specified event has actually come to pass, then we are required to apply this alternative formula.
All we have to do is simply raise it up.
We consider the probability value that was estimated for a particular event, and then we look at whether that event actually occurred or not. So if you were to assign a sufficiently good, a high numerical value to an event that did indeed take place, then that probability would be considered high.
And that would be quite small.
And by the way, this is essentially 0 that would consistently be 1, so we are left with the only relevant term, which is 0.8. But imagine, for example, you did a poor job in that model and you stated that the probability of a certain event occurring is only 0.1.
So if you were to raise that to the power of 1, you would then just get 0.1. Therefore, considering this significant difference, our objective is to maximize these values.
And if you combine these numerical values either by adding or multiplying them, you will certainly arrive at this particular result.
In this particular instance, we're not multiplying because we are taking the natural logarithm. So let's proceed to the second observation. Regarding the second observation, so we obtained the value of 0.3 and the event did not occur.
We take 0.3 and it is raised to the power of 0. Then we multiply this entire expression by 1 minus 0.3, which is raised to the power of 1. What this essentially means is that if we were to assign a lower probability,
if an event didn't happen, it signifies you performed exceptionally well, and that would be considered a very high achievement. And if that value were to be high, it would indicate that the chance of you arriving at this point or the likelihood is increasing. So we can take all these individual numerical values and condense them into a single overarching concept. What you do is take the natural logarithm in each case and then you simply add them up. The higher the number, it means we are assigning higher probability to events that actually occurred and lower probability to those that did not happen. If you are carrying out that operation correctly, then that numerical value would be fully maximized and it would consistently grow, becoming higher and higher. This is exactly what we were referring to when we spoke of the log likelihood function earlier.
we estimate these coefficients to determine the log likelihood value that we obtained at the end.
So we assign a higher probability to the outcome that actually materialized, and conversely, a lower probability to the event that did not occur.
And we accomplish this by utilizing all of our historical data. So we are, essentially fitting the predictive model. We're fitting a model to get the coefficients. So we obtain a higher probability for the days or periods where we had events, and we obtain a much lower probability for particular days, for specific periods, or for entire months,
for which the specific event in question did not actually take place. And we are undertaking this process in the most efficient and optimal manner to maximize the overall likelihood, the numerical value that we previously demonstrated to you.
So this discussion focuses entirely on the binary choice models, such as the Logistic and the Probit. And we can implement this approach by utilizing the Finance Research Gate website. Our data will consist of a monthly time series spanning the period from the year 2000 up to 2024.
We begin by looking at Series A. For this analysis, we chose the stock's monthly return, which serves as our primary variable, and then we specifically picked just one particular firm.
So, for example, let's consider a scenario where we aim to forecast the probability of Apple's stock achieving a positive financial return, in contrast to experiencing a negative or even a neutral zero return.
So our primary objective, the target we're aiming for, is Apple.
First, we completed the initial step, then applied the necessary filters. We successfully obtained the Apple monthly return. It was properly constructed.
Subsequently, we successfully activated our Series B funding round, and as a direct consequence, we achieved the expected market return. And then we proceeded to activate Series C. This was done specifically to acquire the other important X variable, which we refer to as the 6-month momentum. So we're going to activate Series D, and that particular series provides us with the standard deviation, which is essentially our primary measure of market volatility. And then for Series E, we're specifically looking at the logarithmic monthly trading volume data.
So we've gathered all these variables, which will be acting as our primary X variable. To ensure the model is truly dynamic, as we previously mentioned right at the beginning of our discussion, we also need to obtain the lag
related to y, so we can make the model significantly more dynamic.
So we carefully entered and processed each one of these regression analyses. Then, as the next step, we proceeded to construct a comprehensive unified dataset. After we have finished constructing every single series, it becomes absolutely essential for us to begin the detailed estimation process. In the previous version, all information was displayed instantly. For example, if you were to create a series, all its components would be automatically tracked and made visible. However, in order to significantly enhance the overall efficiency of the application, and crucially, to save a considerable amount of time, we ultimately determined that it would be necessary to construct a complete combined dataset exclusively at the very end of the process.
Instead of doing that every series, we do that one time.
Once you've completed that step, we will then proceed to build a comprehensive combined dataset. At that point, we'll possess all the necessary information. Following this, we'll utilize the lag creation box. And then we included the lagged Apple stock return as an additional explanatory variable, bringing our total to 5 or possibly 6 independent variables. Our focus has now shifted to a specific area concerning discrete choice and binary outcomes, which is the subject of this particular section. As a crucial initial step, it becomes necessary for us to convert the y variable into a binary representation.
Currently, the y variable is a continuous one, representing Apple's monthly stock return. We need to convert it to 0, or 1 based on a benchmark of 0. Above that point, we consider it positive, meaning success. That's a 1. And below that, it's negative, so we assign it a 0. We're creating a binary system.
So in this case, we only have two values after creating the binary, whether it's 1, positive, or 0, negative. We then utilize that particular data point as our primary dependent y variable. Subsequently, we regress this variable against a set of multiple independent regressors.
And after doing that, we also ask the application to provide the fitted value, which we did.
So we're presented with two main choices, the Logit and the Probit, and really, these two are quite similar, almost identical. We are trying to estimate the probability of whether the event will occur or not. The only difference lies in the distribution assumed when deriving that probability. First, let's begin by considering the Logit. It's important not to forget to assign a name to the fitted value, since we will definitely be utilizing that in the very next step. Following that, we will then proceed to fit the binary model.
Now, if your primary interest is simply in acquiring the model itself, meaning the actual coefficients, then your work will be entirely finished once we have compiled the table of those coefficient estimates.
So here we have the Logit value. The market return, as you can see, is positive. This outcome is entirely expected, meaning that if the overall market return is higher, then it's highly probable that Apple's return will also be higher. It's really as straightforward as that.
Also, the coefficient here makes sense, referring to the momentum.
If the momentum for Apple's performance over the past 6 months is stronger, it suggests that the company's financial returns will be greater, and indeed, we can expect them to be positive. This is precisely why this outcome is so important.
Concerning the volatility, well, this report here indicates that the volatility will most likely cause Apple's returns to drop into negative territory. Irrespective of the magnitude of the negative value, the likelihood of encountering a negative outcome will increase when there is greater volatility. So what about the trading volume? In this particular instance, the trading volume is not entirely clear, as the statistical significance, for example, is quite small.
Regarding the lagged return, we simply cannot depend on it in this situation because, once more, the associated probability is quite small. Therefore, it makes no real difference whether Apple's return in the previous month was positive or negative.
That particular factor won't really have a major impact on the likelihood of experiencing either a positive or a negative outcome over the course of the upcoming month.
And then we successfully managed to get everything recorded. Now, in order to have a more visual representation of the predicted value and the actual one, then we can
You'll use this section. This section, located at the very end, will allow you to select any variable you need, including any newly created variable, to download that data into a CSV file.
So you go here, you load the selected item.
Variables.
And that will give you the complete version, not just a small sample, but the entire thing.
So, if you want a separate platform to work on, you can download that using a CSV.
So when you press this, that will give you the Excel or the CSV file, which is very similar to Excel's, and you can then work with that. For example, I did this.
And I've obtained this particular file. Now, what's important is that this file won't provide me with a specific fitted value for y, since that's not what we're currently interested in.
What we're interested in is the probability once we transform the fitted y value into a probability, and we have those here.
And then we also have to consider the actual fact of whether this particular event truly occurred or not. The event itself is defined as having a monthly return that is equivalent to or shows a positive value.
For example, the upper return we've been tracking in this specific case was indeed positive.
And what was the probability that was estimated? Exactly. It came out to be 0.735. So is it considered a really good thing now that we obtained higher values for the 1 and lower values for the 0?
The answer is indeed yes, and that's precisely how it should be, because when we performed the model fitting, we employed the maximum likelihood method, which allowed us to obtain the coefficients.
So when we apply these to obtain the fitted y value, it then provides us with a higher probability for the event when it actually occurred compared to when that event did not occur. This therefore represents an in-sample fitting process.
We take into consideration the actual historical observations that have been made, and then we carefully select the coefficients that will ultimately maximize the overall success rate. And the success rate, which is a critical metric for our analysis, is now demonstrating a much higher value of probability attached to its potential outcomes. An event occurring and a significantly lower probability that the event will not take place. So that's the current prediction, isn't it? That's what we've already established. But what we truly aspire to achieve, what we really need, is a robust out-of-sample forecasting capability.
In order to achieve this, we then need to properly fit the new predicted regressors to our established model to accurately determine the fitted y value, and subsequently, we can then transform that resulting probability. However, the data we are currently working with here is strictly in sample. What we estimated is in sample only from 2000 to 2024. In each month, yes, we have a probability estimated versus the event, whether it occurred or not. And overall, it appears that the performance is quite satisfactory. This outcome is to be expected, primarily because we actually performed the estimation in a maximum likelihood fashion. Therefore, we carefully fitted the model based directly on the data we had observed.
And you can make use of the log likelihood equation that we previously outlined for the purpose of your calculations. This one.
So I'm going to be using the f value function. If this particular scenario is the event, then you'll need to use this specific equation, and that result will then represent this part.
But if the probability of the event is 0, then we completely reverse the entire situation. For instance, in this situation, we assigned a low probability and the actual event turned out to be 0. This means we did a good job because we didn't assign a high probability, and that would have resulted in a large number.
So, whenever we achieve good in sample fitting, that specific number will be greater, regardless of the event's actual occurrence.
And once we had taken the log, specifically the natural logarithm for each individual period, we then proceeded to add all of them up. Now it's a negative value. That is entirely expected, and that's precisely how it should be, because we are taking the natural logarithm. It wasn't showing us negative earlier.
It was positive. But because we applied the natural logarithm to a fraction, the outcome will definitely be a negative number. So if you observe a higher numerical value, that indicates our model is performing quite well.
But higher than what precisely? That is the crucial question. Higher than what?
In this specific scenario, it's absolutely essential that we obtain a baseline log likelihood number. This particular log likelihood value will be precisely derived from a statistical model that does not incorporate any regressor variable.
So if you go above that level
to our regression model,
This one. Now, if we were to estimate this model again, but we then proceed to remove the x, or perhaps the lagged y, which of course is just another x variables, and then if we make sure to keep the intercept. If we're completely on our own, and we're both performing the very same task, what do you anticipate the log likelihood number will actually be? I can tell you, it will most certainly be significantly lower, perhaps something like minus 198. Absolutely, that's for sure. Why? Because with more regressors we can achieve a better fit. This allows us to build a superior model that will predict whether the event occurred or not using the historical data we possess.
So, by its very nature, with an increased number of regressors, we are going to achieve a higher log likelihood value.
So, the core idea here is that this is based on the null model, which only includes the intercept term, meaning that no regressors are present. And then we compare this against the one where we actually incorporated the regressors.
Is the difference truly significant or is it not? To do that,
we simply calculate the difference between the values and pause. If that difference is found to be substantially large, pause, it then clearly indicates that we have developed a truly significant, a very good and robust model. You simply need to take the difference, then multiply that result by 2. This will then provide you with the likelihood ratio statistics. If that particular value is large, it indicates that we have a statistically significant model.
The model, the binary model that we are employing to accurately determine the probability of the event either occurring or not occurring, is proving to be quite effective. It is in fact quite effective.
so that concludes our broadcast for today. Thank you for listening.